Okay, let's continue. And this is a very short section. So it will be dealing with load testing and structural health monitoring. First, we'll talk about load testing. Load testing is, as I said, we're not doing an experiment of testing a structure to failure. What we do is we just try to put some loading into the structure so that we can know what characters of the structure is and how they respond to the loading. Like, for example, it's very typical when we design a bridge. We want to know, like, if, for example, we have multiple girders, and when we want to know when the truck comes to the bridge, how much the live load will be distributed into one particular girder under that bridge, under that truck. And the old ASHTO has an equation which is just simply say, okay, it's a function of a spacing of girder. The larger the spacing, the more load will be distributed to that. But that's just way oversimplified. Like, we all know that if you have a very, very short bridge, like if you have very short bridge and you have many, many girders, and when the truck comes here, these girders have very much no impact at all. But if you have very, very long bridge, and when the truck comes, like, most of the girders will be having similar deflection. They will be shear loads very uniformly. And that's why in the new ASHTO, there's a mathematical equations to calculate how live load will be distributed into each girder depending on the characters of the deck, geometry, and so on. Again, just like a deck, for example, if we have very, very weak deck, like, for example, we have timber deck, when the truck comes here, because timber is so weak, the other girders will have no impact. Just one girder deflect a lot more than the others. When you have very, very strong deck, like very thick concrete deck, because the deck is so strong, they will force all the girders to deform uniformly. That give you much, much better distribution. Again, that is because when people develop ASHTO equations, they have to do a different scenario, do different testing, and then they have to develop an envelope to basically just cover all the basic and most like common scenarios. And by doing an envelope, typically you introduce a lot of extra safeties into that. So that's why it's not very accurate if we use ASHTO equations. And we have a lot of scenarios. Like, for example, there's a state in the United States called Pennsylvania. Pennsylvania is a huge state. I think it's much larger than Costa Rica itself. But the population is relatively small, so that it does not have enough tax space. In other words, if you don't have a lot of people to pay tax, and also these were not very high-paid states, so the income level is low. So the state government will not be able to generate that much revenue to maintain these bridges. So when they do low rating, a lot of bridges were rated less than 1, even for the operating level. And then they may say, hey, look at this bridge, and this bridge has trucks every day, and this is like 40 years old. We have 40 years of trucks come, and I don't see any problem. Why you say I need to replace it or fix it? So in reality, that if there's no problem in the past 50 years, the chance of having problem is very slim in the next 10 or 20 years, unless the structure deteriorates. And if the structure does not deteriorate, it should be the same, of course, unless the loading increases in the future. But and that kind of scenario, that's why ASHTO said that if you believe your bridge is okay, you can have another avenue to manage your bridge, which is the load testing. So load testing very much has two components people must pay attention. One is how live load is distributed. Once you do a test, that will be relatively easy. You just bring a regular truck. It can be any type of truck. Of course, if it's very similar to design truck, that will be good. But if not, it just designate the spaces, and you know the total weight, and each axis of the weight. It just asks truck to park, stop and park there. It just measure the stresses of all these girders, and then you will be able to know how these live load will be distributed into that. Typically, you measure the stresses and deflections just to have more. The reason we collect more data is that later you need to play around. And also, that's one thing, how they are distributed. Second thing, that there's an impact, as I said. The impact of live load is almost 30%. And you know that most likely the impact is not that, typically it's like 10 to 15%, it's less than half. So if you have that deduction, effectively you increase your loading capacity by rating factor by 20%. That's a very, very significant improvement. You can also do a test. You just have a regular truck, just pass by it, and measure the stress or deflection, and to see, compared with static load, to see what magnitude of magnification is. In other words, if a static is 1.2 and you get 1.5, which is 1.5 divided by 1.2, that will give you how much dynamic impact component is. And so these are two fundamental things. Once you have these things, and then you can develop your finite element model based on that. How you develop finite, because finite element model typically have like a longitudinal elements, which will be your girders and plus your deck, and these are elements. And transversely typically you have diaphragm and the slab. If you had, it just basically just cut. Yes, you assume you're cutting slab into segments of, like, for example, 1 meter each. You have like many transverse beams, and then you just put this into your model, and then you put it, when you do the finite element analysis calculation, you will see how much deflection of each girders, and then you just compare it with your testing, see the discrepancies usually don't match. So what you do is you manipulate the transverse member stiffness. Like once you modify this transverse member stiffness, then you will be able to match your finite element deflection and stress and your actual testing. You can because it tests that's collected a lot of data. You cannot match all. It just uses like a mathematical equation, or just using visual inspection of, basically just try to have best fit. Once you have best fit, then that will be a model, so that you can, using that new model to calculate actual stress. And usually you will be able to achieve that goal. And another thing that actually, it's very, very controversial. A lot of old bridges can be designed as non-composite. By non-composite, I mean there's no connection between your girder and your deck. Like, for example, if it's a concrete girder, the concrete, you don't have a stirrups go into the deck. And if you have a steel beam, you don't have like a shear studs to connect to that. So usually we call non-composite. Many old bridges are non-composite. And virtually all the new bridges are composite. Because really in composite, you have much bigger section and much larger capacities. So for non-composite, typically when you do the finite element model, you just use a net section. And if you want, you can add a deck section. But if you add these two pieces like eyes together, it's very small. But if we assume it's composite, then the section modulus is much larger. So that's why a lot of people, when you do like a regular calculation, you assume it's non-composite. But in reality, when you do the test, you can measure this like a stress or strain actually at each section for a couple of points. And then once you have points, you can draw a line, and you will know where the neutral axis is. And most likely the neutral axis is not in the middle of the steel or concrete girder, so it is much higher, so you may have a bigger component of concrete deck composite with it. And so normally you will use that as your finite element model. And another thing, that's to the model. The real tricky thing is that what happens when you do calculate capacity? Because if it's designed as non-composite, all you have is a net section. And if you add the concrete into this equation, then your capacity was actually much, much larger than before. And that may explain why there's no problem with the deck. Actually, some people explore that possibility and say, okay, maybe I just use it. Since my load test indicate actually it's composite section, because my neutral axis is much higher. So when I calculate, I have equivalent of much concrete deck with it. So my bending, when I calculate my bending, my concrete deck is part of a compression zone. So, and originally at the beginning, I said that, well, that's not very good approach, and it's very unsafe approach. So later, a lot of people say, Jim, you know what? Like when you design a reinforced concrete beam, do you assume like a reinforcement and concrete that are bound together? I said, you have to. Like if reinforcement and concrete have no bonding, there's no capacity. Because the whole thing of reinforced concrete is based on the common deformation or common strain. In other words, assume like plane strain to develop equations, and that's typically true. You say the same thing, like if the concrete slab and concrete girder does not separate, they have sufficient bonding. Even if you don't have reinforcement connect them, they're bonded. And they say, well, if the bridge is 50 years old and they still did not fail, like due to longitudinal shear, so the chance of they fail in the next 10, 15 years is very slim. So they say, I should be able to use that. So I think it has logic. So typically when I do evaluation, I don't use that as an argument to significantly increase my capacity. I only use a load test to modify the impact and modify how live load is distributed. But if somebody say, okay, my capacity is also enhanced by load testing, actually, no, I think I would not be against that idea. I think really depending on like if the bridge is old enough and there's no sign of any like a longitudinal shear failure, I think chances are they'll be fine. They have enough bonding between the deck and the girder. So basically, that is the whole concept of load test. Like if you understand what I said, probably you don't need to go further. But I'm good through that anyway. The load test again is not meant to do the failure. Actually, we did have such thing like. This is in China. In China, most of these bridges are relatively new, like about 10, 15 years old. And like one highway, they want to widen it. Instead of they widen the bridge, they just remove all the bridges. And then one of the universities in China, they said they want to do a load test to see how their design code, how accurate the design code was. And so they calculate how much uniform distributed loads will be. So they put concrete bags and then put enough, and the bridge did not fail. And the professor said, well, it doesn't work. Just take off the concrete, put rebar. Rebar is much heavier. They just keep on adding rebar, and the test finally failed. They found that actually the actual capacity of a bridge is much, much higher than the design strength. And that explains why a load test is a very good avenue to save costs. In other words, if you don't see problem, most likely you will not facing the problem. Of course, if you don't do a low rating calculation, it's just simply do inspection, probably you will not see problem in the first place. Again, candidate for load testing is that if you see a bridge and when you do calculation, it says not safe. But in reality, it is safe. So in that kind of situation, probably you can do a load testing. And also, like some kind of bridges, it's difficult to analyze. And like for example, if you have a two arch, and the two arch has a deck on top. And typically when you do the design calculation, you look at, see, like if I simplify, if it's a two-lane bridge, and you just assume how far the truck can go to one side of arch. And then you just look at, you put the truck as close to the right side of arch. And then you just simply assume one arch is simply supported, another arch is supported. And you put here, you say, okay, this is 75%, that reaction 25%. Then you just say that truss should be designed for 75% of that bridge. But once you do the load test, you find, because the truss arch is so long, if you put the truck even close to here, and you say that actually only takes 55%, that will take 45% instead of 25%. So you don't need to design for much larger live load than necessary, because it's so complex and it's not simply we put the truck close to here. This is like it's not like simply supported beam. You put load here, you know how much reaction each has, because it's a three-dimensional thing. So basically, just the steps of doing that is, first step is just try to put a load and so measure the stress. But basically, you cannot measure stress, you measure strains. You can calculate back to stress, or measure strains or deflections. Sometimes you just try to measure as many things as you can. Because once you compare with finite element model, you want to have best fit. So once you have best fit, you have more data, you can fit better. Step 2 is do a preliminary analysis of data to see, like for example, you look and measure the strain to see how much concrete deck should be part of the composite sections. And then develop a finite element model based on the initial, like original design. And then you just analyze that and simulate the actual load data. So by manipulating these, typically you manipulate transverse members. The reason transverse members can be manipulated is, like when you do finite element analysis, longitudinal is very much, because longitudinal member is very long. When you cut them into pieces, it does not affect too much. Transversely, when you cut deck into small pieces, you lost a major component of rigidity, which is the deck's ability to twist. Like once you cut off, it's almost like timber deck. No, you cannot twist it. So that's why you can change the characters of these data in any way to represent the reality of this deflection or stresses. Then compare, once you have best fit, compare the test data and just change these characters, and then you got a very a best fit situation for strains and deflections, and then just use that model to actually calculate find the bending moment, shear forces of these girders and so on, and that will give you more realistic. And actually, that's very strange. Like once I've done that and I do a presentation to the bridge owners, they always have the same question. Hey, Jim, oh, your model is so accurate. I look at your model outcome and your testing outcome, they are so similar. I said, yeah, they're similar because I use that test model to manipulate my stiffness of different elements. So then after that, you use the exact same equations to calculate. And that's one component. A second component, again, the second component is that I. Once you do load test, you will find I is not close to like 33% or 1/3 of live load. Again, like if that does not work, like if that does not work, and like for example, if you are tested, like I is 20%, for example, it's a relatively short. The shorter the bridge, the bigger impact there because they're more likely to match the bridge. The truck vibrations. Then you can actually put the reduction sign and say, okay, like for example, if it was 100 kilometers per hour speed limit, you say that to put the 80 kilometers of speed limit. So when you do a load test with 80, you get much smaller impact. Then you can use smaller impact and that will work. So all you need to do is put the speed restrictions at the bridge. Okay. So these are very much two independent. So, and the questions for load testing. The concept is very, very simple. Just try to do a test to use that accurate data of deflection stress, like strength, and sometimes you can also detect like a vibration frequencies, and then you use finite element model to best fit all these outcome of data you tested. And then once you've done that live load distribution factor for individual girders will become individualized. You know, once individualized, it will not just an envelope. So that will give you much accurate prediction of how much live load will be acting on that particular element. And that typically will reduce your stress significantly or approaching to the reality of the stress. As health monitoring is another topic, which is because these two topics are so short, I put them together, so they are not related that much. Health monitoring is very, very good concept. Like for example, we don't go to see doctor every day. We go to see doctor if we feel a pain. Like for example, if we have a pain in your lung or heart, you go to see doctor. And the reason is that when somebody creates human beings, as humans created, there's such a monitoring system in our body so that we can monitor ourselves. Like for example, if you have a pain on your leg, and you go to see it, you say, well, you have something in your joint you need to remove. So somebody may say, well, what if we let Bridget tell us if the Bridget has problem? Just like human being can feel something is wrong. The Bridget cannot. So they develop, they say, okay, let's put a monitoring system. So let Bridget tell me if something is wrong, so we can do an inspection for that particular. So I don't have to do inspection every year, every 2 years or so on. That is very, very wishful thinking. And that can maybe one day become reality, but right now it's not a very good approach economically. I'll tell you why. Basically, that's a concept, just so that the system can tell something is wrong, so we can go to see it. And so there's sensors. So the sensors typically had to be installed when the bridge was built. If you install sensors after the bridge is built, it will look ugly. You will have a lot of different sensors put on the bridge. People will look at, and also will be damaged easily. So these sensors have to be designed during the design phase and constructed during the construction. And typical sensors are either GPS-based or like strain-based. Strain-based is like typically optical, like fiber optical based. With low test, structure testing here, laboratory, which we know all kind of different sensors and instruments. So, for example, people may say, okay, like for example, for that cable stay bridge, they say, well, let's put some sensors on these cable stays. So, for example, if this cable is actually made of like multi-strain cables, just like force tension cables, and you say if someday a couple of strain is broken, then if a couple of strains broken because the force is the same, then the stress will be different, or the elongation will be different. All of a sudden, that if I have a fiber optic sensors, strain sensors from here, and if that's broken, so you may have bigger elongation somewhere. And or if I have a steel box girder, and I put here, and all of a sudden if there's some other crack, especially if it's concrete box girder, and if it's crack, then my strain all of a sudden bigger will give a warning signals. So that's a very good concept, but in reality is that these sensors don't last long. Typically, the optical sensor can only last about 20 years. Most of these sensors were made in Germany, 20, 25 years. And these bridges are typically built for 75 years, 200 years. Some may be built for 120 years. And anybody studied, everybody have been to business school here? Okay, nobody goes to business school, so it's easy for me, so I can say anything I want. But anyway, there's a model, if you study safety or reliability of manufactured product, one of the very, very simple model they call bathtub model. Like for example, if you buy a car, very often when you buy a car, you had problem in the first month or something, and that's because a manufacturing defect. And if you don't see problem in the first 6 months, the chances you have a problem in the next year or so is very, very slim. So the probability of mechanical failure is very, very high at the beginning, and it goes down, and it will keep low. And here for typically cars after 4 or 5 years, getting higher and higher. That's why they give you warranty for 3 years or 5 years. They know if they give you warranty for 10 years, every car will have problems. They will have big consequences. So we call it bathtub theory. The same as for bridges. If you don't have problem in the first 6 months, the chances of having problem in next 10 years or 15 years is very, very slim. So you don't really need, unless you have initial problem. And when you really when you really have potential problem in 50 years, 40 years, these sensors are not working anymore. So that's why it's totally, not totally to me, it's a waste of effort or resources. That's why in the United States, it's not popular, but in Asia, it's very popular. But I talked to a lot of bridge owners. The bridge owners, well, everybody's doing that. I should do that. I don't really care about cost. But if I don't do it, I have problem. How do I explain to my supervisor? Say, why didn't you do it? So if I have that same system, and then if I have a problem, I can easily explain. These contractors did not do good job, or the designer didn't do good job. But anyway, that's the reason. Another reason is when you detect something, like for example, if the elongation or position based, like for example, if you want to know how much movement due to the wind load, you can measure the movement, or you know how much deflection due to truck load. And because every day the truck load or wind load is different, you get the outcome, but you don't know what truck is there or the wind load there. So there's no meaning for you to tell if that bridge is problem. Like for example, yesterday the maximum deflection is 20 centimeters. Now today I got 21 centimeters. Is that a problem? People say maybe not, because we just have more trucks simultaneous on that bridge than yesterday. And so that's small. And for example, and can you really tell if that, for example, if I have post-tension bridge, can you tell when the crack may happen? You never know. You put a lot of strain gauges, and you hope to catch where the crack is. Like for example, if there's one crack in that strain gauge, that strain gauge may all of a sudden have a much larger elongation, then give you a warning. But unless you have complete everywhere, it's impossible to really predict. So you may just like strategically put some locations and hope for catch. Again, that's location-based and loading-based. And since you don't know these two things, there's no way of really have good concept. But there's another measurement which is very important, very good, like in my knowledge, like which is vibration-based. We all know the magnitude of vibration is related to loading, but the frequency of vibration has nothing to do with loading. Everybody agree on that part. If you study like structural dynamics, you should, or even study physics, you should have learned that part. So in other words, if I for example, if I put a if I put a vibration sensor on that main span, and the vibration you can measure because this is not simply supported structure. It has many redundancies. When you have many redundancies, they have different mode of vibration, different shape of vibrations. But basically, they are the lowest frequency vibration we call it base vibration, and then there's the second, third, and so on. So the total vibration is a combination of that. Now the computer can actually isolate vibration. Actually, it's very not difficult. It's just mathematically to get like first frequency, second frequency, third frequency vibrations. So if the structure has no changes, this vibration frequency should not change. Every day should be the same. And if, for example, one day you have a big crack in a girder, then all of a sudden the stiffness is reduced. Of course, you may measure the deflection a little bit, but the frequency is suddenly reduced. So like if the base frequency was 3.1 megahertz, now just hertz, not megahertz, 3.1 hertz now become like 2.9 hertz. You know something changed all of a sudden, and you know probably something is going on. You may do a really detailed inspection. That's why I think if you do want to do a measurement, that vibration frequency sensor is most important. And these are a lot of many examples. Actually, I participated in a couple of designs of these, but I personally don't recommend people do these. But a lot of professors like that. The reason professors like that, because for complex bridge, there's really no building code. So each each design team develop their own design code. For example, how much wind load can be. They say, well, let's do a model. So they build a similar situation of the river condition. They put like buildings in similar situation. They put it in one wind tunnel, and then they using wind tunnel to test to see how these structures behave, and using that data to design. And everything else is the same. Because all bridge, like ASHTO using design code is only for short and medium span bridge. For long span bridges, it does not cover. So each agency will define its own design criteria. And after that, once you have these sensors, it will give you a feedback of how accurate your original design assumption is. And then every time you do that, you can write a lot of research papers. So these things can be improved because when I look at design calculation, when I look at actual testing, that will be the differences and so on. So it has a lot of research values, but does not give enough value for bridge owners. As I said, there's benefits, of course, but the benefits compared with cost is the ratio is very low. So these are the different sensors and different locations positive. And the stress monitoring, cable force, and the different things can be modified, can model different things. Again, the dynamic, even for like a suspension cable, for example, suspension cable, and it has its own vibration frequencies. So if we imagine one day some cable is broken inside, then the vibration frequency will change. Yeah, these are basically just monitoring of these frequencies. So the frequencies should be just keep on the same. That should not change. Temperature monitoring is typically, they also use sensors, and the temperature and the wind can also be monitored. These are typical bridges, how many sensors and different type of sensors were installed, and it's like sensor locations, and basically these are the design sketches. And typically these sensors will have a wireless collections, because these are continuous collected. So they have a central collection server, and then this server will use the internet or like a Wi-Fi type of wireless go to a remote receiver. That's typically, but in China, it's different. In China, each of these bridges is considered a company. It's collect tolls. Although it's owned by government, typically they will register a company for each bridge, and they set up offices and also toll facilities. So then this data can just link to the offices with high-speed internet. And actually, these are the data. Like one day, there was a big impact of. These are just for research purposes. That's assumed movement and the real movement. These are all the data collected. Yeah, any question on this? I don't think most people will need to have any design for these type of things. Again, typically I don't recommend to have these kind of sensors installed. It's very, very expensive. Like typically, a bridge, just the sensor itself is more than between $10 million to $50 million, that range. It does not give you very good return because they don't last, as I said, they typically don't last for very long.